All right, welcome everybody to today's mathematics class. Please take your seats so we can get started. And while you're busy finding a seat, let's do a couple of warm-up questions and tweet back. True or false question. For each matrix game, the payoff of the row player and that of the column player always sum up to 0. Is that true or not? Give you 30 more seconds to answer that. All right, let's take a quick look at your answer. So most of you think this is false. The payoff of the row player and that of the column player do not generally sum up to 0 for a matrix game. The correct answer, of course, is according to the definition of a matrix game, that this is actually correct. So you remember a matrix game is defined to be a zero-sum game. And zero-sum means one player gets what the other pays. So they pay off in total, so it sums up to 0, right? Second question. If that is true, then is that the following true or false? Every matrix game has a value of 0 as the net payoff over both players is always 0. Right? One gets a positive payoff, the other gets the same negative payoff, so the value is 0. Is that true or not? Let's take 30 more seconds. All right, so here's the results. About a quarter of you said this is true. And of course, the majority is correct. This is false. Please don't confuse the notion of value and zero-sum game. Right? A zero-sum game means one player gets what the other has to pay. So one payout is positive, the other is negative, and they sum up to 0. The value is the expected payoff for the column player. And that is usually not 0. It might be 0, but it doesn't have to be. And it doesn't have a lot to do with the notion of zero-sum games. Defining a value only makes sense for matrix games because we have one payout matrix that governs the payout of both players at the same time. So they're somewhat comparable. If you have a bimatrix game, the payoff for both players might be totally different and unrelated. So then it doesn't really make sense to define something like a value. Yeah, that only makes sense for a matrix game, so for a zero-sum game. But the value is not generally 0. And you all remember we've seen some examples yesterday. A value of 0 basically means in the long run, if they repeat the play over and over again, the payout of both players will be approximately 0. Right? So in the long run, no player gains something and no player loses something, and a game like this is what we call a fair game. Basically, everybody has the same chances of getting a payoff. But that doesn't have to be true in general. All right, final law question. Again, true or false? For each matrix game, the payoff for the row player is always negative. Is that true or not? I sure hope that's an easy one. Let's see. Let's take 30 more seconds. All right, so here's the result. Most of you said this is false, and most of you are correct. The payouts for a matrix game are pretty much arbitrary. So when I set up the game, I can decide on which payoffs I want, which payoffs I think model the situation and attend most appropriately. And of course, if the column player has a positive payout for some situation, then the row player will have a negative payout of the same absolute value. But I could reverse the situation if I wanted to. Yeah? So that doesn't really say anything. Okay. So enough about the warm-up, I guess. We have one more section to talk about, but before we do that, I'd like to quickly take a look back at our penalty kick game that we discussed yesterday. So you remember we talked about penalty kick in soccer, where the penalty taker has 2 actions available to him. He can either kick to the left or to the right, and the goalkeeper has to decide which side of the goal to guard. And then we defined a payoff matrix like this, where if both choose the same side, then no goal will be scored, so the payoff is 0. And if both choose different sides, then the penalty taker will score a goal, so he'll get a payoff of 1. And in this setup, the penalty taker is the column player, so that is the payoff matrix from the point of view of the penalty taker. Okay, we discussed searching for Nash equilibrium MTO strategies, and basically we did this by going over all the possible choices and seeing if we found anything, and we didn't. Then we discussed how to compute optimal strategies, and we did this via this linear programming approach here. And let me maybe mention one thing. There have been a lot of questions on computing optimal strategies in bimatrix games. We only discussed this in the matrix game setup for a good reason, because it's much more challenging in the bimatrix game setup. The problem here is, for a constraint like this to make sense, we basically were optimizing over the payoffs of both players at the same time using the same matrix. We just say one of them is maximizing, the other is minimizing, right? So in this case, this is the column player's linear program. He maximizes his expected payout. And the constraints, those make sure that the payoff will never be less than this new here, regardless of what the row player does. And this is only possible to formulate in this way because both the row and the column player use the same payoff matrix. It's just that one maximizes, the other minimizes. In a bimatrix game, they have different payout matrices, and those may not be related in any clear way. So we won't be able to formulate this in NLP of that form here, right? We can't have both these payoff matrices in the same constraint, basically, and having one minimized and one maximized. That doesn't work anymore. And that's what complicates the situation considerably. So I just leave it at that point to say that we'll not discuss the situation and it will not be relevant for the exam. I'd only expect you to be able to compute optimal strategies for matrix games. All right, if you're interested, we can take this up at some other point. Maybe when we have time at the end of the semester. Yeah, and finally, we solved that LP here, right? So we set this LP up for the situation at hand. And we solved it using a simplex approach. Went through this, took quite some time. And we got the solution that most of you would probably have guessed. And it's nice to see that this actually works. So optimal strategy is to randomize uniformly over both strategies. Of course, the idea is neither the goalkeeper nor the penalty taker should be predictable anyway, right? If the goalkeeper knows that the penalty taker favors the left side, then of course he'll guard the left side more than the right side, and he can use that as an advantage for him. Penalty taker doesn't want that to happen, so his best choice is to just randomize uniformly between those two strategies. And the payoff is then 1/2. Question? This is the matrix game, yes. Okay, so the question is this a matrix game, and does AR have to be minus AC? And the answers is yes and yes. So this is a matrix game, and actually AR is minus AC. So this here is AC, the column player. The column player is the penalty taker in this case. Right? And this is the same as the negative of AR. And R is a goalkeeper in our analysis here. Right, so we capture both payoffs in one matrix, and by convention, we always state the payoff matrix of the column player. And what we say here is, well, either no goal is scored, then both get the same payoff of 0, or goal is scored, and then the penalty taker gets a payoff of 1, and the goalkeeper gets a payoff of -1. Yes? Sorry, how do I solve for the optimal values without the simplex algorithm? Well, two possibilities basically that I could think of. The first one, you could check if you find a Nash equilibrium pure strategies, basically by going through the possible options and see if there is one. And of course, if you find the Nash equilibrium, that is also a pair of optimal strategies, and you can deduce the value from that. It might not be the only pair of optimal strategies, but if I'm just asking for one pair of optimal strategies, that's it. And usually that's the question that I would ask. Or you can use the LP and then try to deduce an optimal solution by, well, looking at it intelligently. Sometimes it works, right? So if you look at the numbers, you might find the only way we can get an optimal solution is setting this variable to that value and this variable to that value, and sometimes some reformulation helps. So for easy LPs like this, this is usually also an option, not doing simplex, but just writing down the LP and then doing some analysis and some argumentation, getting to the optimal solution that way. But of course, the simplex is the approach that will always work, but that would probably take most time. Yes? So if in the exam I ask you to check whether there is a pure Nash equilibrium pure strategies and find it, then yes, you need to write down some argument for that. Unless I specifically state that I don't want an argument and just the Nash equilibrium. But that will be in the problem statement, right? Okay, any more questions about this at this point? Otherwise, let's briefly take a look To the extension, we've also briefly discussed, or maybe one more word about this here. So we also find out the value is 1 over 2. So that means the game is not fair, right? On the other hand, if we look at the possible actions, there's 4 possible outcomes of that game, 4 possible combinations of actions, right? And in 2 of those 4, the goalkeeper prevents the goal. In 2 of those 4, the penalty taker scores a goal. That seems pretty fair, right? Everybody has a 50% chance of achieving his or her goal. Why is it that the value is not 0? Yes? Yeah, exactly. Let me just copy that. That didn't work. Just a second. Try again. Okay, maybe not try again. Just write it down once more. Okay, so this is the payoff matrix that we used. And you will notice this payoff matrix is unfair already. Right? This is the payoff matrix from the point of view of the penalty taker. And the point is the penalty taker can either win something, right? Like, for example, in this situation or in this situation. Or he can lose, but if he loses, his payoff is 0, right? So he doesn't really have to give anything. He doesn't really have to pay anything. He can gain, but he can't really lose. And that's the problem here. The payoff matrix that we used is kind of balanced in favor of the penalty taker already. The penalty taker can only win, and the goalkeeper can only lose. Right? The best thing the goalkeeper can do is he could get a payoff of 0 maybe. Best thing the penalty taker can get is a payoff of 1. Worst thing he can get is a payoff of 0. And that's where this 1/2 comes from. Basically, that's the middle between 0 and 1, which are the 2 possible extremes in our payout matrix. We could also have chosen to model this differently, and actually someone suggested that. One other possible way to model this is to make it symmetric and say, well, there's always a payoff of 1. If the penalty taker scores a goal, then he gets the payoff of 1. If the goalkeeper prevents a goal, then he gets a payoff of 1, right? A prevented goal is as good as a goal that you scored. You could also take that point of view, and if you did that, of course, the game didn't really change, right? The properties are still pretty much the same. It's just the numbers, the payoff that changed a little. All the Nash equilibria will still be the same. The optimal strategy will still be the same. The only thing that will change is the value. And if I do that, I will get a value of 0. Right? So the value that I get in the end highly depends on the numbers I put in my payoff matrix. And if that is already skewed in favor of one of the players, then probably the whole game is skewed in favor of that player. All right? So just as an aside, and then one more thing that we also discussed towards the end, and that I've asked you to think about. What if I add a new strategy? What if instead of just being able to aim for the left and the right part, I could also aim for the center? And of course, the goalkeeper then also has the option of guarding the center. Right, so every player now has 3 possible strategies. And of course, I can easily adopt the payoff matrix to that situation. And I could say, well, if the goalkeeper guards exactly the position that the penalty taker is aiming for, then there will be no goal. So no goal in these cases here. Otherwise, the penalty taker would score a goal. So in these other situations, there'll be a 1 here. And again, as an alternative, you could replace the zeros by -1s if you'd rather want that. It doesn't really matter. And my question is, what is now the optimal strategies for the goalkeeper and for the penalty taker? And what is the value of the game? Does that change? And I do hope some of you took some time to think about that. Maybe let's first talk about the optimal strategy, because that is something that should be easy to guess, even if you didn't prove it. Let's take a minute to see on TweetBack whether you have a good idea of what that optimal strategy could be. Here's a couple of options. Take a minute to answer. And if you haven't thought about it, maybe try to take a guess. All right, 10 more seconds. Okay, let's take a look. So here's the results. And predictably, most of you guessed correctly. The new optimal strategy is, of course, again, to randomize uniformly, because if you don't randomize uniformly, obviously, your opponent will take advantage of that, and that's always bad for you. So in this case, 1/3 for each strategy is the optimal strategy for both players, once again. And once again, it doesn't have to be the same for both players, right? It is in this example, and in many other examples, surprisingly many, because the situations in the game are often somewhat symmetric in a certain informal way, but it doesn't have to be that way. Okay, so that's the optimal strategy for that game. Optimal strategies, 1/3, 1/3, 1/3 for both players. And now the next question is, what is the value of that game? And even if you haven't thought about that at home, you should be able to compute that now that you know the optimal strategy. So let's take 2 minutes or so, see if you can find the value of that game. And for those of you who have an answer, I have opened a tweetback quiz, so please try to answer with the correct value for the game. We take 30 more seconds. All right, let's take a quick look. So here's your answers. Most of you said 2/3. 1/3 comes in at second place, and while the rest, I think we can ignore that. Rarely someone thinks the value will stay at 1/2, so either it decreases or it increases. Maybe let's think about which of those seems more likely. Before, we argued that the game is pretty much fair apart from the valuations that we put on the outcomes, but each of the players has a 50% chance of winning in a way, yeah? What about this setup here? Well, now we don't have 4 situations that are possible for combinations anymore, but instead we have 9 possible combinations. In 3 out of those 9 possible combinations, the goalkeeper wins by preventing the goal. In all other possible situations, the penalty taker scores a goal. Right? So intuitively, I'd say introducing this third possible strategy has increased the chances of the goalkeeper. So the value should change in his favor, and, sorry, not the goalkeeper, in favor of the penalty taker, of course. So the value should change in favor of the penalty taker. Penalty taker is the column player. Right? So remember, the value is the expected payoff of the column player in optimal strategies. And that means I would expect the value to increase. It was 1/2 before, so it should be higher now. Right? It can't be more than 1, of course, and that is reflected in the choices, because 1 is the maximal payoff that you can get in this game. So I guess it's going to be somewhere between 1/2 and 1. So with these 2 options, 1/3 and 2/3, I would lean toward the 2/3. Let's see if we can prove that. And I already said the value is the expected payoff. So if we already know the optimal strategy pair, we can just use that to compute the expected payoff, right? So the value here is the expected payoff. So with the optimal strategies that we have, let's call them Y star and X star, we can just compute that by taking y star transpose times a times x star. That's the expected payoff if both players play these optimal strategies, y star and x star. And these strategies are exactly the ones that we have here. Just to answer one question that has popped up, I didn't actually prove those were the optimal strategies, right? I hope you thought about that at home. And of course, one possible way to prove that is, again, set up the LP, compute the simplex algorithm, and as an outcome, you'd get these optimal strategies. If you need more simplex practice, might be a good idea to try that at home. Might also take some time. All right, but just if you have those already, just computing the value should be easy. We have the matrix here, right? So what we have to do is, that's 1/3 times this vector. That's the optimal strategy for the row player. Then here is our payoff matrix. And this is the optimal strategy for the column player. Now I can just move those 1/3 together. That's 1/9 times 1, times, and this matrix times this vector, that will yield 2, 2, 2. So what I get is 1/9 times 2 plus 2 plus 2, that's 6, 6/9. And I can factor out 3 here, so that's 2/3. Right, so that is the value of the game, and those who voted in favor of 2/3 were correct. Good, so as expected, introducing this third strategy skews the game in favor of the penalty taker. Right? It became much more likely that a goal was actually scored with these 3 strategies. And of course, in modern soccer, there's not only these 3 strategies. A goal usually also has corners that can be guarded and aimed at. So if you have a good penalty taker who's able to aim precisely for one of the corners, there's even more strategies than that. And if you analyze that situation, I think you can guess what happens. The game will be skewed in favor of the penalty taker even more. All right, so I guess that concludes the discussion of this example. Any more questions about this before we move on? Yeah. What's the difference between value and payoff? So the value is the expected payoff if both players play their optimal strategies. The payoff is usually the payoff for a given specific situation. Yeah, so you can only talk about the payoff, either meaning the payoff matrix, that lists all possible payoffs for all possible action combinations. Or you can see, given a pair of strategies that need not be optimal, what's the payoff for these pair of strategies? Yeah, and if those happen to be optimal strategies, then the payoff is the same as the value. All right, let's take a quick look at the questions here, because I think there are some I wanted to quickly answer before we move on. Aren't zero-sum games just a specific type of matrix games? The answer is no. Zero-sum games are a specific type of bimatrix games. Right? Not every bimatrix game is a zero-sum game, but those that are zero-sum games, we call those matrix games. It's just another name for zero-sum game. Yeah, it's shorter. That's why I prefer that name. Skew symmetric. We talk about skew symmetric in just a minute. Will we be expected to use the simplex method in the exam? The answer to questions of this type is always, of course. Don't bother asking that again. I mean, why would I take the time to discuss that? Is every matrix game a zero-sum game? That way, yes, that is correct by definition, simply because a matrix game is defined to be a zero-sum bimatrix game. Okay, are we also allowed to use different strategies to find a mixed strategy Nash equilibrium without doing linear programming, but instead a method we found somewhere else? 2 parts to the answer. In general, of course, you are allowed to use different strategies to get your answer. but you'll have to provide a sound argument for that. And usually a sound argument would be, that's the way we did it in class. If you're doing it a different way, you'd have to argue why this is actually valid. And sometimes it's easy to argue. For example, if you have an LP and you're not solving it by the simplex algorithm, but instead you make an argument about the only possible solutions or whatever, that's 1 or 2 sentences, might be sufficient. And you'll find examples for that in the suggested solutions as well. And maybe we'll get to doing one of those kind. On the other hand, if you're using some completely different approach that we've never even touched, then you'd also have to provide an argument, or even better, a proof for why this actually works, if it's not obvious. Right? So in general, yes, you're allowed to do that, but you'd have to argue why your approach works. And again, of course, this is only true if I ask for a justification in the problem statement. If I explicitly say, just give me the answer, I don't care how you got it, then any approach is fine, I don't care, and I don't want to know. Question? Yes, so this thing we calculated here is from the perspective of the penalty taker. Penalty taker is the column player in our setup, and usually in matrix games we only look at things from the point of view of the column player. From the point of view of the row player, basically it's the same thing but with a minus sign, right? The payoffs of the row player are the same but negative. So, sorry? Oh, it's not supposed to be 1/3 for the other player. No. No, absolutely not. So the point is, the value of the game is the expected payoff for the column player, right, in optimal strategies. The optimal strategies are, of course, for the column and for the row player. We computed both. They happen to be the same in this case. They don't have to be. So if we say the expected payoff for the column player is 2/3, then basically that means in 2/3 of the attempts, the column player will actually score a goal. The expected payoff for the row player is then minus 2/3. Because by definition, the payoff of the row player is negative that of the column player. Yeah, so his expected payoff is also negative the value. Yeah, so that's why the expected payoff for the row player would be minus 2/3. Yeah, in 2/3 of the situations, the goalkeeper is not able to prevent the goal, and for each goal that the penalty taker scores, he gets a payoff of -1. Does that answer the question? Great. Yeah, so please don't confuse that. Yes, one more question. Go ahead. So the question is, do we have to use simplex in general, or can we use a simpler way for a 2x2 matrix? But that doesn't really matter for the answer. You can use a different approach. That's totally fine. If you can make an argument for why the optimal solution has to look like this, that's absolutely fine. And for 2x2 matrices, this can often be seen pretty easily, I agree. Yes. Yep. So if you only have 2 strategies, then of course, if one has probability p, then the other will have probability 1 minus p, and that simplifies things considerably. So you probably will be able to devise an easier argument for why the optimum looks a certain way. Yes. So you can do that. And I also did that in some of the suggested solutions for that sheet. You'll see that later on. All right, where was I? Let's skip over that. I think I answered that. And I'll have to go over those in just a bit. Okay. So let's talk about the last section of this week here. And that is called symmetric games. And symmetric games are, again, matrix games, but a very specific type of matrix games, right? So you'll remember we started with bimatrix games, then we considered a special situation, zero-sum bimatrix games. We defined those to be matrix games, so just a different name. We found out how to analyze matrix games, how to compute an optimal pair of strategies, and how to compute Nash equilibria. And our symmetric games are, again, a very specific sub-situation of matrix games. And the definition is very simple. A matrix game with quadratic payoff matrix is called symmetric if the payoff matrix is skew-symmetric. And skew-symmetric, you remember, that means the transposed is equal to the negative matrix. Right? So basically the entries of the matrix are mirrored along the diagonal. A positive entry on one side is reflected to a negative entry on the other side. And the diagonal entries itself have to be zeros. Right? So that's a skew-symmetric matrix. And the game is called symmetric if its payoff matrix is quadratic and skew-symmetric. Okay? And we're interested in that kind of specific situation because it simplifies the analysis quite a bit. Because for a skew-symmetric game, or a symmetric game, the following holds. First, x transposed a times x is always 0. So if I have one strategy that is played by both players at the same time, their payoff will always be 0. The value of a game like this is always 0. So a symmetric game is always fair. Other games can also be fair, but for a symmetric game with a skew-symmetric matrix, I know it's going to be fair without doing any computations. I just have to look at the matrix. And finally, if I can find a strategy for a column that has this property, so AX is greater or equal to 0, then just using that strategy for both players is a pair of optimal strategies and thus also a Nash equilibrium. Right? So it might be a lot easier. I might not have to solve a linear programming problem to get my optimal pair of strategies. Instead, I just have to find a vector that has this property. In general, of course, it might still be basically the same amount of work, because if I can't find it by any other means, like guessing, then I might still have to solve a linear programming problem to find a vector that satisfies this. But it might be easier to just look at the matrix and then hopefully take a good guess, see if that works. Yeah? Or if I provide you with some vector and the task is prove that this is actually an optimal strategy, this is the only thing you have to check if the game is symmetric. Okay, here is an example for a very well-known symmetric game. It's called rock, paper, scissors. I trust you all know rock, paper, scissors, so I don't have to explain that. Here's the payoff matrix. So both players have the same strategies called RP and S, rock, paper, and scissors. If both use the same action, then it's a tie, so no one gets a payoff, 0. Paper beats rock. So if column plays paper and row plays rock, then the payoff is 1. Rock beats scissors. So if column plays scissors and row plays rock, then the payoff is -1, and so on. I'm not going through details here. The rest is the payoff matrix that you get when you go through the rules. And you can easily see the diagonal here is all zeros. And all entries can be mirrored along the diagonal. And the respective mirrored entry is the negative of the original, right? So this is a skew-symmetric matrix, because A transposed is equal to -A. That means rock, paper, scissors is a symmetric game. That means we already know the value is 0, so the game is fair. and any strategy with this property will be an optimal strategy for both players. Right? So what we now do is we try to find an optimal strategy by looking at this set of inequalities here. If we write that down, it looks like this. And if we reformulate that slightly, we get these three inequalities here. And now a little trick to get to the right solution in this case. We take these three inequalities and try to put them into a chain of inequalities, right? So we start with this one, x1 is greater or equal to x2. Then we chain this one, so here's an x2, and we know x2 is greater or equal to x3, this is the green inequality. And this one, he starts with x3, so we can put that at the end, x3 is greater or equal to x1, sorry. So we have formed a chain of inequalities that starts and ends in the same point, in x1. So the beginning and the end of the chain have the same value, and that of course means everything else also has to have that same value, right? Otherwise it can't work. If x2 is strictly greater than x1, we'll never get back to x1 again. If x3 is strictly greater than x2, we'll never get back to x1 again, right? So we'll have to stay at x1. And that means all of these values are equal. And as we also know they sum up to 1, of course the only possible outcome is we need to have 1/3, 1/3, 1/3. And probably, again, that is what you would have guessed, right? It's randomizing uniformly over all three strategies that will turn out to be optimal. Okay, so that's an example for a symmetric game. Now maybe let's have a look at some other problems. And again, a symmetric game is a special situation of a matrix game. Not every matrix game is symmetric. And in particular, not every matrix game that has value 0 is symmetric. Right? That doesn't have to be the case. For example, think of that penalty taker thing where we replace the zeros by -1s. Then we got a value of 0, but still that game is not symmetric, simply because the diagonal of the matrix is not 0, can't be symmetric. Right? So there are non-symmetric games that have a value of 0. Every symmetric game has a value of 0, but not necessarily the other way around. All right. So let's take a look at an example. Let's see, which one shall we use? Looked at that one already. Yeah, maybe this one here. So that's from a 2019 exam. Maybe I should actually display that. It's a lot to write. Let me see if I can find the sheet. Yeah, that should work. That's my penalty kick situation. Here it is. I'll copy to the notes just a second, but you can already try to solve that. It's a lot of text, but don't be scared. The solution is actually not that complicated. So we have the following game here. 2 players, the row and the column player, will simultaneously choose a number out of the set 1, 2, 3. We'll say NR and NC are those numbers. And then the payoff is determined according to the following rules. If both players choose the same number, the payoff is 0. So that's tie, basically. If the numbers are different, and the difference is equal to 1, so one number is 1 higher than the other, then the player with the lower number gets a payoff from the other player, and the payoff is determined by the numbers that they chose, NR plus NC. If the numbers are different and the difference is not equal to 1, then the player who chose the higher number receives a payoff, And the payoff is determined by the difference in R minus and C absolute value. First task, determine the payoff matrix of the game, and then it will look a whole lot easier. So take a couple minutes to do that. And meanwhile, I try to copy that to the notes so that the people following us online will also get a chance to look at that. volume seems to increase, so I'm guessing most of you are nearly done. Maybe let's take one more minute. All right, so let's see what payoff matrix you have devised for that. So obviously the strategies that we can play are 1, 2, 3 for both players. So in the situation that both play 1, what is the payoff? 0. And of course, same is true for both play 2 and both play 3, right? That's the first situation here. If both players choose the same number, the payoff is 0. All right, let's take a look at the next one. So if the row player plays 1 and the column player plays 2, what's the payoff? Any suggestions? Yeah? -3. Anyone doesn't agree? You'd say +3? Okay, let's see if we can find out. Okay, row plays 1, column plays 2. So in which situation are we? And R and C are different, obviously. And the difference is equal to 1. That's also true, right? So we are in this second situation here. The player who chose the lower number, that is in this case the row player. Row player chose the lower number, 1. The column player chose 2. The player who chose the lower number gets NR plus NC. So NR is 1, NC is 2. It means the payoff must be 3. NR plus NC is 3. And the player to receive that payoff is the row player. And remember, the matrix, the payoff matrix for a matrix game is always from the point of view of the column player. So if the row player gets 3, that means the column player has to pay 3. So the right payoff is -3. All right? And of course, you can look at the reverse situation right away. So if the column player plays 1 and the row player plays 2, setup is almost the same, but now the column player is the one with the lower number, so he gets the payout. Right? That means in this situation we have a +3. Okay? Similar situation here. Let's say row plays 2, column plays 3, then the difference is again 1. So again, we're in that second case. Again, the row player has the lower number, so he'll get the payout. And it will be an R plus NC, so this time it's 2 plus 3, it's 5, right? So here, Here we are. The column player, no, sorry, the row player gets the payoff, so the column player has to pay, and he has to pay 5. So the payoff is -5 here. And in the reversed situation, the row plays 3, column plays 2. Column would get the same payoff, so it's 5 here, +5. Okay, and that leaves us with these two fields here. So what is the correct entry here? 2. Is there anyone who disagrees? Apparently no. Yeah? -2. At least we can agree on the value, on the absolute value. So let's take a look. So here, row plays 1, column plays 3. The difference is not equal to 1, so we are in the third situation. The player who chose the higher number receives the payout. The higher number in this case is the column player, so he will receive the payout, and he'll get the difference, and R minus NC, the difference is 2. And as column will get the payout, that means +2 is the correct number here. And again, situation is reversed here, basically the same, but now the higher number is with the row player, so he'll get the payout, and that means column has to pay. So there's a -2 here. Okay, so this is the correct payoff matrix for this game. Next question. Determine the value. Is the game fair? Give a justification. And if the exam question is stated in that way, give a justification. That means if you just write down 42, you get 0 credits, no matter if that's the right answer or not. Okay, so let's see if you can find out what the value actually is. I'll give you a couple of minutes to think about that. And I even have a quick tweetback question on, is the game fair? You can vote on that one. Just a quick show of hands. Who is done with the answer? Who needs more time? That looks good. I'll give you 30 more seconds then. Should be more than sufficient. All right, so here's your answers. Most of you said the game is fair, and most of you are right. What's the justification for that answer? Why is the game fair? Yep, that's it. Yeah. So the correct answer would be the matrix A is quadratic and skew symmetric. As you have probably seen from the way I devised the values of that matrix. And that means the game is symmetric. And that means the value is 0. And that means the game is fair. Right, so that's a completely valid answer for that question. You don't have to do any more computations. Just look at the matrix, see that it's skew-symmetric, so the game is symmetric, so you know the value is 0 and the game is fair. Please don't forget to actually make that statement, right? So if you just write the value is 0, that will probably earn you 0 credits, or close to 0 credits at least, because I'm asking for a justification. Some people gave a justification in their answer in this way. They said the value is 0 and thus the game is fair, or the value is 0 because the game is fair. That is, of course, also not sufficient. Right? Why would the value be 0? Why would the game be fair? You have to prove at least one of those to be able to deduce the other. So what you have to mention somewhere is the matrix is skew-symmetric and thus the game is symmetric. And that's why we know the value is 0, and that's why we know the game is fair. Okay? So finally, one more question here. Show that the mixed strategy X star given as 1/10 times 523 is optimal for both players. Again, let's take 2 minutes to show that. Is there a question? Yeah, so instead of writing A is quadratic and skew symmetric, you could also write A transposed is minus A. Don't forget the transpose, please. Yeah, so that's same thing. As usual, quick show of hands. Who's done? Who needs some more time? 2. Let's give it 1 more minute then. All right, so let's take a quick look at how to answer that question. Show that the mixed strategy given here is optimal for both players. What do we have to do to confirm that? Well, what did you do? Yeah. Yeah. So, sorry? Yeah, you can do that. It's even a little easier in that specific case here. So here, you remember we have a symmetric game. And you'll also remember for symmetric games, we have that specific condition here that says if a strategy has this property, AX is non-negative, then this is already a pair of optimal strategies. In this case, I can plug in both and I'll get the value that's correct, yeah, but this might even be easier. Yeah, so what we have to do here is we just have to compute A times X star and see if that is actually greater or equal to 0. If it is, then we have an optimal strategy. All right, and that is of course easy to do. We just plug it in here. 523 times 1 over 10. And we get, well, 1 over 10 doesn't really matter much. And here we get, let's see, this is minus 6 plus 6. This is 15 minus 15, and the third row will give us minus 10 plus 10. So nicely enough, that is an all zeros vector, and of course that is greater or equal to 0. So as the game is symmetric, that means X star is a pair of optimal strategies. Right? So once again, if you have a symmetric game, try to make your life as easy as possible. Exploit those properties if you can. Maybe it's not an advantage, maybe you still have to do some computations, but you can at least give it a try. Should be quick to try that out, and if it doesn't work, well, then it doesn't work, then you'd have to resort to some other method. Question? Right. Yeah, exactly. So you could also use, just compute the payoff, right? I mean, the optimal strategies must yield the payoff, so you can do something like compute X transposed AX like that, and you get 0, obviously, in this case. So that's a strategy that realizes the value, so it's an optimal pair of strategies. Okay, I think we have time for just one more quick practice question. Let's just scroll this down a little. Again, I'll copy it to the notes in just a minute. Well, let me quickly explain. So we've discussed the game rock, paper, scissors, and there's a lot of variants on this game. 2 of those are on the exercise sheet. Here's the third one. That's called crash, rock, paper, scissors. It's basically the same as rock, paper, scissors. The only exception is that rock is now much heavier and really destroys or annihilates the scissors. So rock scores double against scissors. That means the payoff matrix is modified in this way. So if rock is against scissors, the payoff is not 1, but 2 in favor of rock. Right? So here's the payoff matrix, and the task is, as usual, determine the value, the corresponding optimum strategies, and a Nash equilibrium. And of course, the third point should be the most interesting part of that. So see if you can solve this in the remaining almost 10 minutes. Quick show of hands, who's done? 2. Okay, maybe 2 more minutes so that I can give you at least the idea of that. All right, let's have a quick look at how we can approach this problem here. The first question for the value should be pretty easy to answer. As you will hopefully all have seen, this is again a zero diagonal, and again we have this property that the transposed matrix is equal to the negative matrix, so the matrix is Q-symmetric. So the game is symmetric, and that means the value is 0. Okay, so that should be quick. That also means if you want to find an optimal strategy, what we can do is we can just have a look at AX and then see if we can find a strategy where this is greater or equal to 0. Right, so if we compute that, we get x2 minus 2x3. We get minus x1 plus x3 here, and 2x1 minus x2. And we want that to be greater or equal to the all zeros vector. So we obtain 3 inequalities. We have first inequality is x2 is greater or equal to 2x3, right? I just reformulate them slightly. Second inequality is x3 is greater or equal to x1. And the third one is 2x1 is greater or equal to x2. And you've already seen with rock, paper, scissors, we adopted the strategy to chain these together to prove that all values in the chain have to be equal. And we can do a similar thing here. Maybe take some playing around to see that is, how this actually works. First thing we can do is we can multiply this by 2, right? This is the only one that doesn't have a 2, but of course we can multiply that by 2 and then it will contain a 2. And if we do this, we can obtain the following chain of inequalities. We start with this one here, and we start with the smaller side, so 2x1 is less or equal to 2x3. Then we have a 2x3 here, and we can chain this together because 2x3 is less or equal to x2. And finally, we have an x2 here. So x2 is less or equal to 2x1. And that means we start and end with 2x1. So all the terms in this chain of inequalities have to be equal. Right? So what that means is 2x1 is equal to 2x3 is equal to x2. And now again, all of these, so x1, x2, and x3, will have to sum up to the value of 1. So what do we get here? Well, if they sum up to 1, and we know that 2x1 and 2x3 are equal to x2, that means x2 is twice x1 and x3, and those two are equal. Right? If you want a sum of 1, there's only one way we can get that. x1, x2, x3. Well, x2 needs to be 1 over 2, and x1 and x3 need to be 1 over 4. Right? So they sum up to 1, and 2x1 is 1/2, which is x2. 2x3 is also 1/2, which is x2. Right? So that's the solution here. And I think that's a little surprising. Remember, that's the probabilities for rock, paper, and scissors. So even though rock is now twice as strong, at least against scissors, we actually end up playing it less than in the original game. Right? Remember, I had a probability of 1/3 in the original game, and now we only played with the probability of 1 over 4, whereas paper is now played half of the time. Yeah, so that's the optimal strategy in this case. And to see that it's optimal, all we have to do is when we have to state that this here obviously satisfies this greater or equal to 0. So that means that is a pair of optimal strategies for our symmetric game. All right, so that's the analysis of crash, rock, paper, scissors. You can practice more on that on the exercise sheet right now in the upcoming exercise sessions. Just one small remark. There's lots of questions on Tweetback that I haven't had the time to cover yet. I'll try to answer all of them online. If you find the answer is not satisfactory, then please let me know. Write to the forum, write to the Tweetback again. I'll leave it open for some more time so that you can answer to the question or just post a new question. And we'll hopefully be able to take the time to discuss those at some later point in the semester. All right, so I'll see you in the exercise session.